Thank you very much. So I'm looking at the SAM because I think that's quite important, and sea ice extent. But I'm looking at this in a seasonal time scale. So we're looking at SAM anomalies in the austral summer, so December, January, February, and then trying to examine how those anomalies are causing sea ice changes in the following months. So in particular, during these months of sea ice growth, do we see an imprint of the December, January, February SAM on what happens to sea ice there? And sea ice in the Southern Ocean undergoes this enormous seasonal cycle. So here we've got the February and September sea ice extent contours, and we can see that we grow and lose about 15 million square kilometers of sea ice every year, which has enormous implications on how the atmosphere can communicate with the ocean and on the ocean itself. By melting and freezing the sea ice, we're changing the stratification, and we're also changing things like the surface albedo. Now, if we look at the time series for the SAM, as Matthew said, it's been increasing, but this increase has been particularly in December, January, February, driven by the ozone depletion. So here we've got the different months. In red, we've got summer, and then the others. And what you'll notice is that we have this general increase in the summertime SAM, but just the summer that we've just come out of has had a very negative SAM. And so what I'm going to try and show is that I think this negative SAM that we've just had is linked to the sea ice extent decline that we've just seen in a zonally integrated sense. So rather than talking about regionality in sea ice, I'm going to be integrating across the entire southern hemisphere and trying to understand how these changes are being driven by SAM. Now going back to this figure, the colors are showing us the zonal wind, the climatological roaring 40s. And you'll notice that most of those are outside the limit of sea ice extent. But in particular, when we have the summer months where the sea ice is really close to Antarctica, we have the whole Southern Ocean exposed. So if we wanted to pick a time of the year where we could force the ocean with the atmosphere, that's a great time. We've got nothing in the way. The wind just blows straight over the ocean. So we can impart heat fluxes, we can impart momentum fluxes. And what happens to the ocean after that then is going to impact on the sea ice growth as we go forward. So this is a very simple equation to describe sea surface temperature anomalies driven by the SAM. So what we have is the anomalous westerly winds here, Torx, which are driving an Ekman transport. So Torx divided by rho naught F is giving us the meridional transport. And when we have anomalous westerly winds, that's pushing water to the north. When we have anomalous easterly winds, it's pushing water to the south. And this water is moving across a climatological gradient in sea surface temperature. So as the water is moving north, it's going into regions where it's colder than the surroundings. So it's giving us a negative anomaly. And once we form this anomaly, it then decays away with some sort of decay time scale, which here is given by lambda. And if we expand that lambda a little bit, there are lots of different processes that go into affect this. In particular, I'm focusing on two here. So we have atmospheric damping, where the atmosphere is either taking the anomalous heat out of the ocean or putting heat back into an anomalously cold sea surface. The rate at which this happens depends on a number of factors like latitude and season, but also the scale of the anomaly. If the anomaly is very large, then as the wind blows over it, it warms up or cools down, and so only the edge of the anomaly is experiencing that fresh wind. The other term that I've got here is entrainment. So this is subsurface effects in the ocean. As the mixed layer deepens, it's mixing with the water underneath the mixed layer. So if we have a temperature anomaly in the mixed layer, that then gets diluted as we proceed from summer through autumn into winter, and the mixed layer deepens. Now, if we take the SAM time series and we detrend it, and then we take a sea surface temperature product and detrend that as well, what I'm showing here is some composites where we've taken the years with large positive SAMs and large negative SAMs, and then calculated the sea surface temperature anomalies from those years. So it's the positive composite minus the negative composite divided by 2. And what we notice is a very large annular band of cooling around Antarctica. So this is the anomalous Ekman transport pushing water away from Antarctica against the climatological gradient. The sea surface temperature climatology is shown here in the contours with a 1 degree centigrade contour interval. And although we have this very widespread cooling, there are some regions where we do see an anomalous warming in these SAM events. And as we'll see later on, that also has an implication for the sea ice growth in those regions. Now, this is in February, so this is the end of the summertime SAM, December, January, February. This is the maximum anomaly that we see in this system. And if we follow that through for several months to the May, you'll notice, first of all, that the colors have decreased. So this temperature anomaly has been damped out by the atmosphere and by entrainment below the mixed layer. But we still have a largely annular cooling, if somewhat weaker. Now we can look at the temporal evolution of this anomaly more clearly by integrating between 50 and 70 degrees south and taking the zonal integral in there. Now I've shown the two composites separately here, just so that you can see that the same things are happening in both cases. This is essentially a symmetric impact. But the negative anomalies have been multiplied by -1 so that they overplot. Now, the initial anomaly is about 0.15 degrees C, and we see that that decays away on a time scale. And there's been some work looking at what the time scale might be for the Southern Ocean, with some people suggesting something about 3 months. So if we overplot some exponential decays, the line in black is a 3-month decay time scale, and the line in gray is a 2-month decay time scale. And what you'll notice is that it essentially decays away with a 3-month time scale. So we start with this temperature anomaly, and then it's decreasing over time. So what I want to know is this temperature anomaly A, large enough, and B, sticking around for long enough to impact the sea ice extent throughout the ice growth season? So if we repeat the composite analysis, but this time on sea ice concentrations, in February we have this picture, and it's not particularly annular in structure. We have large positives and negatives, and we have these ice losses around the region where we had warm sea surface temperature anomalies. But in general, particularly around the eastern Antarctic, there's more ice growth than there is ice loss. And as we follow this through for several months into May, you'll see that it's predominantly ice growth following these cold sea surface temperature anomalies. But that this signature of some loss around the Antarctic Peninsula persists. In particular, we're seeing ice growth around eastern Antarctica and the eastern Weddell. Now, to compare the time series of this ice extent changes, we can do the same sort of zonal integral that I did with the sea surface temperature. And we have the two composites here. I've kept them in their correct signs. So what we're seeing is less ice following a negative SAM and more ice following a positive SAM. So these anomalies are about 0.3 million square kilometers, which is a fairly small fraction of the seasonal cycle in sea ice extent, but these are statistically significantly different from each other. What's particularly interesting is that we see a maximum in the anomaly in March, April, May, so during the autumn, the ice growth, and then that anomaly decays away as we proceed through the year. Now, these are based on composites, so we've disregarded all of the years that don't have largely anomalous SAMs. So anything with a sort of small SAM has been disregarded from this analysis. But if we use regressions, then we can keep all of the years in the data set. So here we're not just cherry picking out the ones that have big signals. And what we see is a very similar response. So this is telling us how much sea ice we grow from a 1 sigma SAM event in this detrended SAM time series. And again, you'll notice that March, April, May, we have the largest impact, and then that impact is decaying away with time. And as we proceed through to the next summer, the error bars become much larger. So as well as looking at this in observational products, we can look at it in a coupled climate model. So this is exactly the same analysis, but done in the GISC coupled climate model. So this is a 1-degree ocean with sea ice and an atmosphere, and a SAM anomaly imposed every December, January, February. So this model has an ozone hole equivalent to the mid-1990s that just repeats every year, year on year. And what we see is that SAM anomaly gives us some initial ice extent that again is peaking around this ice growth season and decays away with time as we proceed through the year. Now, doing these kind of composite and regression analysis is really fun. It gives us a great example of being able to look at the variability and also the error bars. But it's nice to plot the individual years so that we can make sure we're not doing anything silly with the statistical analysis. So what we have here are individual years from the time series, and they're color-coded by their SAM in this detrended SAM time series. And what you'll notice is that we have predominantly purple for positive SAM anomalies up here, and predominantly orange for negative SAM anomalies. Now, there's obviously a lot of scatter, but we can see essentially the same result that we saw in the composites and from the regression analyses. We see that we get this anomaly, that negative SAMs tend to lose ice. This peaks around April, May, and then decays away as we proceed through to the winter and then the following summer. Now, at the start, I mentioned that we'd had this very negative SAM that we've just finished. And so, based on this analysis, we'd expect to have lost some sea ice. And using the regressions, we can say that for every 1 sigma of the SAM, we should be losing a bit over 0.1 million square kilometers, which means that here we should expect an anomaly of about 0.5 million square kilometers. The actual time series data show that we've lost much more ice than that. So this mechanism doesn't explain all of the sea ice loss that we've had recently, but it does explain some of what we've seen. So just to conclude, we see that the December, January, February SAM gives us an impact on the sea surface temperatures, which is very well established. We know that this anomaly in the sea surface temperature then decays away some sort of timescale that appears to be about 3 months. That sea surface temperature anomaly is both large enough and persistent enough to give us an observable impact on the sea ice extent. And we see that positive SAMs during the summertime give us more sea ice for the following few months, but that this effect decays away by the time we come back to the next winter. So what this is saying is that although we're seeing a seasonal impact, this doesn't explain the long-term trends, except on a very seasonal basis. For every summer that we have a large positive SAM, we expect slightly more ice in the following autumn. So thank you very much for your attention.
Time for questions.